going to talk about section 10.5 today, which is talking about counting problems that involve not and or. So what we're talking about with this is counting techniques that can lead thought of as indirect techniques. Correspondence, we're going to look at the correspondences between set theory, logic, and arithmetic, and the good example here is this chart. So with set theory, if we were talking about something that is not in the set, we're referring to its complement. If you are not sure about some of the stuff, you might want to look back at chapter 2. So the complement is the apostrophe. And again, with set theory, that represents things that are not in the set. And then we have the union symbol, which is the letter U, or the U. And the union symbol represents joining all the things together. And then we have our logic notation. And with logic, the tilde represents not. So if we put the tilde in front of the P or the tilde in front of the Q, then that represented not something. The or symbol, or the union symbol in logic, is the V. In arithmetic, if I want to take something away from a set or take something away, I use the subtraction symbol. And if I want to join everything together or add things together, I use the addition symbol. So that's what they mean by the correspondences between set theory and logic and arithmetic. So what we're looking at here are, sorry, mouse was slow. Okay, so what we're looking at here is some of the information about set theory that we want to talk about. I'll wait for my slide to catch up. There we go. All right, so here's how we're going to deal with this. If I have a Venn diagram, the U represents the universal set, which is all of the possible values. If I have a set A within that universal set, then A complement are all the values that are not in the circle A. So I know that if I take all of the A values and the A complement values and put them together, I will end up with the universal set. I'll end up with everything. So what we have here, when we're talking about the symbol for N, we're talking about the cardinal value. And what the cardinal value means is how many things are in that set. And again, this information is in chapter 2, so if you're unsure about any of it, you can go back and refer to that information. So again, the symbol N means cardinal value, and the cardinal value is how many things are in that set. So what we're saying here is that if I take all of the values in A, which are things that are possible, and all of the things in A complement, which are the things that are not possible, then if I add those two things together, I get the universal set. And then I can manipulate these sets, and I can say if I take the universal set and I take away A complement, then I'm left with A. So all I'm doing is using my arithmetic to manipulate the set theories and the set notations that we're getting here. So the next couple things are actually some information from chapter 2 that I wanted to do a quick review because there are some questions that deal with proper sets in this section. And a proper set is defined this way. A set A is a proper set of B if A is a subset of B, but A does not equal B. And the symbolism for a proper subset is given to you here. So what we're looking at, this is the symbolism for proper subset. There is no line underneath of a proper subset symbol. So for example, if I had a set, let's say that A equals the set 1, 2, and 3, and B equals the set 1, 2, 3, and 4, then A is considered to be a proper subset of B because it contains elements that are in B but it is not equal to B. So A is called a proper subset of B. So to figure out how many subsets there are, we can use this formula. If n is the number of elements that you're given, then 2 to the nth power will tell you how many subsets there are for any given set of elements. Now the thing is that with that situation, there's always going to be one subset that contains the whole set. So we always have to eliminate that one when we're thinking about proper subsets. So the formula for proper subsets would be 2 to the nth power minus 1. So if you'll notice here, here's our formula for proper subsets, and up here, this is our formula for just a subset. So let's look at this next example. I have this set S that contains the letters C, A, L, U, T, O, R. And I want to know the number of proper subsets. So again, if I use my formula, n equals 7 elements, because there are 7 letters in the set. So the number of subsets would be 2 to the 7th power, which is 128. But remember that one of those 128 sets is the set CALUTOR, and a proper subset does not have all of the elements. It's not equal to the original subset. So I have to take the 128 and subtract out the one extra value or the one extra subset, and so there are 127 proper subsets in this set. Okay, so this is just describing that information that we just talked about. All right, so here's another one. If 5 fair coins are tossed, in how many ways can at least one tail be obtained? So we're going to sort of do the same thing. What we're going to do first is figure out what are all of the possibilities, or how many different possibilities could there be. And so we're going to use the fundamental theorem that we used earlier, the fundamental counting theorem, to figure out how many possibilities. So there are 5 coins. So that means that my first coin could be a head or a tail. So there's 2 possibilities for the first coin. There's 2 possibilities for the second coin too. There's 2 possibilities for the third coin. There's 2 possibilities for the fourth coin, and there's 2 possibilities for the fifth coin. So there are 32 total possible combinations of these coins. I could have all heads, all tails, 4 heads and 1 tail, 3 heads and 2 tails, different things like that. The only situation that does not count, because I want at least 1 tail, so the only case that doesn't count, or that I have to eliminate, is the case where there are 5 heads. So what I have to do is take that 32 that I got and subtract out that one possibility that's not possible, and I end up with 31 different possibilities for the number of sets, or how many different ways that can happen. And again, this is explaining that again in a little bit more detail. All right, so here's the same kind of problem. We need to create a committee. This is one of the problems in your book. We need to create a committee of 4 faculty members from a department that has 25 members in it. And how many committees will include the 2 faculty members, Fontana and Spradley? So what we're going to do is we're going to figure out all the possibilities that there are, and then we're going to subtract out the possibilities that we are not looking at. So in this situation, there are 25 faculty members, and we want 4 faculty members in our committee. So we're going to use our combinations that we've been learning, and we're going to do a combination problem. And we're going to do 25, choose 4, because we want to know how many faculty members, or how many groups of 4 faculty members I can have. So that's what we're going to do. We're going to do 25. Hang on here. We're going to do 25 faculty members. Choose 4 faculty members. And that's going to give me all of the possibilities. That's going to give me all of the possibilities that could possibly happen with 4 faculty members in there. And then what I have to do is say I need to subtract out the possibilities that will not include Fontana or Spradley. So that's 23 faculty members that I can choose from. So it's 23 faculty members, choose, again, 4. So here's why we did this again. If I look at all of the possible committees that included all 25 faculty members, there are 25 faculty members to choose from. If I say that how many of the members will include Fontana and Spradley, that means that there's 2 faculty members that we're isolating here. So if I take away the possibilities that do not include them, that would be 23 faculty members I'm choosing from. So if I look at my numbers here, and I did forget to write those numbers down. So if I work this problem out, I will end up with a total of 3,795. Actually, I've got it written out here. That's why. Okay, so let's look at that. So I will have 25 choose 4 is 12,650. 23 choose 4 is 8,855. And so if I subtract those two, because I want to take the possible sets, the total universal possible sets, minus the complement, which are the ones I don't want, and I end up with 3,795 possibilities. Okay, so another thing that you can look at involving this is something that we did in section 2.4. So again, you may need to look back at chapter 2 if you're having some problems understanding this. And what we can do to figure out how many possibilities there are is that we can take all of the elements of one set and add them to all of the elements of the other set. And depending on whether the 2 sets are joined or not joined, we may have to subtract out the overlap. So that's what the intersection is referring to there. So here's our technical formula here. So the first formula, if you can imagine that we have a Venn diagram, and what our Venn diagram looks like is that we have our 2 sets of information, and they're overlapping. So what I'm doing is I'm taking all of the values from one of the set, adding them to the other set, but I'm subtracting out that overlap in the middle because I don't want to include that twice. That's called, that's a set that is not disjoint. Whereas on this example, where I have a disjoint set, here's my set A, and here's my set B, so there is no overlap. So all I'm doing is looking at what's in set A and what's in set B. Okay, so here's what we have here. We've got to decide whether these sets are disjoint or not disjoint. So that's what we have to look at with each of these problems. So how many 5-card hands can I get, a deck of cards, that consist of all hearts or all black cards? And so what we're looking at here is that if you have a heart in a deck of cards, then there are no black cards in there. And if you have black cards, then you don't have any hearts. So this is what we refer to as a disjoint set. Okay? So to figure this out, we're going to figure out how many possibilities are all hearts and how many possibilities are all black cards, and then we're going to add those 2 things together. So in a deck of cards, there are 52 cards. And of those 52 cards, 13 are hearts. And I want to choose 5 cards. So I have 13 cards to choose from. So I'm going to do 13, choose 5. And that will be the number of hearts. And then I want to add that to the number of black cards. Well, again, there's 52 cards in a deck, and half of those are black. So I have 26 possible cards to choose from, and I'm going to choose, again, 5 cards. So if I add these two values together, I will get the total number of possible combinations of my deck of cards that would give me either all hearts in my hand or all black cards. And you'll notice here that there are 67,067 different possibilities for those decks of hands. Okay, so let's look at the next one. All right, so here's another problem. A diplomatic delegation of 20 congressional members are categorized as to political party and gender. If one of the members is chosen randomly to be a spokesperson for the group, in how many ways could that person be a Republican, or how could they be a man? So if we look at this, and if we do the combinations like we've been doing, the Republicans there are 12 Republicans in this delegation. So that's where I'm getting that number from right here. There are 12 Republicans in the delegation. And there are 11 men in the delegation. So what I'm doing is I have 12 Republicans to choose from, 11 men to choose from, but I have to remember that this is not a disjoint group because some of those men are also Republicans, so they're overlapping. So I have to figure out how many total possibilities in the Republicans, how many total possibility combinations of men, and then subtract out that overlap or that intersection. So that's what we're talking about here. So what we're doing, and what they've done it here is using a set theory notation. And what I'm going to do is show you another way using the combination symbolism. And it doesn't necessarily make a lot of sense because as you'll see, but I'm going to go ahead and do it anyhow. You have 12 possibilities, and you want to choose one. And then you have 11 possibilities, and you want to choose one. But then you want to subtract out the 8 possible overlaps, choose one. And so what you end up with is if you put this in your calculator, or if you do the mathematics for this, 12 choose 1 is 12. And 11 choose 1 is 11. And 8 choose 1 is 8. So I end up, if you'll notice right here, with the same formula as if I use set notation or if I use the cardinal values, I end up with 15 possible combinations. All right, so far so good, I hope. All right, so let's look at this one. How many 3-digit numbers are multiples of 2 or are multiples of 5? Okay, so we're dealing with 3-digit numbers. So we're going to use our fundamental counting principle with this. In this case, this is not a disjoint situation. So we don't have to worry about subtracting out those overlaps. So let's look at this. We've got, if I have a 3-digit number, I have 9 choices for the first digit. I could have the number 1, 2, 3, 4, 5, 6, 7, 8, or 9. I cannot have 0 for the first digit. And the second digit, I have 10 choices. It doesn't say anything about the digits can't be duplicated. So I have 10 choices for the second digit, because I could have a 0 for the second digit. Now the last digit, if I'm talking about a multiple of 2, the last digit has to be an even number. So it has to be 0, 2, 4, 6, or 8. So I have 5 possibilities. So for an even number, or multiple of 2, if it's an even number, I have 450 different possibilities. Okay? All right, so now let's talk about multiples of 5. Again, with multiples of 5, I have 9 choices for the first digit, 10 choices for the second digit, but if it's a multiple of 5, it has to end in a 0 or a 5. So I only have 2 possibilities for the last digit. So if I calculate this out, I get 180 possibilities. And these are multiples of 5. And I said a minute ago that this was not disjoint, but that does actually overlap. So the overlap is that some of these numbers are multiples of 5 and multiples of 2. So if we think about those, if we have those types of numbers, again, the first digit could be a 9, the second digit could be a 10, the third digit would be 0, because 0 is an even number, and 0 is a multiple of 5. So that means there's one possibility for the last digit. So there are 90 numbers that overlap. Okay? So what we're going to do is the same thing that we've been doing. We're going to add together the two possibilities and subtract out the overlap. So we're going to take the 450 and we're going to add the 180 and we're going to subtract out the 90 that's overlap, and we end up with 540 possible 3-digit counting numbers that are either multiples of 2 or multiples of 5. And again, this explains that to you again in some other detail. Okay, so here we have another example. So we have a single card. One card is drawn from a standard 52 deck deck of cards, sorry. And first question is saying, how many ways could that card be a club or a queen? So if you think about it, a club could be a queen of clubs. So there is a little bit of an overlap there. So how many different clubs are there? Well, there are 13 different clubs. So for part A, we're going to do 13, choose 1. Okay, how many queens are in the deck? Well, there's 4 queens in the deck. So that would be 4, choose 1. But there's one situation where there is an overlap. So I just have to subtract out that 1, right? I have to subtract out the case where I have a club, a queen of clubs. So again, if I realized earlier, anything choose 1 is going to end up to be the same thing. So I have 13 plus 4 minus 1 means that I have 16 possible cases for A. All right, so then the second case says, how many of those situations could be a red card, or how many different ways could I have a red card, or could I have a face card? Okay, so again, red cards, there are 26 possible red cards in a deck of cards. So we have 26, choose 1. Face cards in a deck of cards, there are 12 face cards in a deck of cards. So 12, choose 1. And there are 6 cards that are face cards and red, because I would have Queen of Hearts, King of Hearts, Jack of Hearts, and I would have Queen of Diamonds, Jack of Diamonds, King of Diamonds. So I have to subtract out those 6 possibilities that are overlaps. So I end up with 26 plus 12 minus 6. So I end up with 32 possibilities that are red cards or face cards. And there's that explanation again for you. So I hope this helps. Hope everything's going all right. You're keeping up with your work. Let me know if you're having any problems, and you can call me or email me, or you can text me. Have a great day.